In this video, we're going to talk about the free electron gas. That's the simplest solid-state system, basically a particle in a three-dimensional box. In fact, we'll start with the particle in a three-dimensional box. Then we'll talk about reciprocal space. Then we'll introduce the Fermi level and the Fermi energy. And finally, the total energy of the free electron gas. And how do you measure properties from that? So, solids are a particular kind of system of identical particles. The simplest model of a solid is the free electron gas. In this model, we ignore all nuclei, we ignore all core electrons, we consider only the outermost valence electrons, we have no forces except for confining walls in the box, and we assume a rectangular parallelepiped box with dimensions L sub x, L sub y, and L sub z. We're going to treat the particles as a 3D particle in a box system. Well, we know that the potential in 3 dimensions then is 0 inside the box for x, y, z, and 0 inside the box, and it's infinity outside. The Schrödinger equation is very simple. It's minus h bar squared over 2m. The Laplacian applied to psi is equal to the energy times psi. And because you have separation of variables in the Laplacian, you can say that psi of x, y, z is going to be x of x, y of y, and z of z. This leads to 3 independent Schrödinger equations, one for the x-coordinate, one for the y-coordinate, and one for the z-coordinate. And each of them looks like minus h bar squared over 2m, d squared x dx squared equals e sub x times the function x. The total energy of this system is simply the sum of the 3 energies, e sub x plus e sub y plus e sub z. And the solutions are, for each of the individual coordinate systems, x of x is equal to a sub x sine of kx times x plus b sub x cosine of k sub x times x, where k sub x is just square root of 2m e sub x over h bar. Same thing with y, and the same thing with z. If we now apply the boundary conditions at the edge of the box, where x, y, and z are equal to 0, the wave function must be 0. That eliminates all the coefficients b, sets them to 0. At the other end of the box, that is L sub x, L sub y, L sub z, the wave function must also be equal to 0. And that introduces the usual boundary conditions, give you quantization. So that k sub x times L sub x is equal to n sub x times pi, and n sub x is 1, 2, 3, off to infinity. Similarly, for k sub y times L sub y is equal to n sub y times pi, and the same thing for z. K sub z times L sub z is equal to n sub z times pi. Now, in principle, Lx, Ly, and Lz are different from each other, and so these are different scales. The total wave function is therefore psi of nx, ny, and z is equal to 8, square root of 8 over Lx times Ly times Lz, which is the volume of the box, times the sine of nx pi over Lx times x, times the sine of ny pi over Ly times y, times the sine of nz pi over L sub z times z. The energy of this system, of the 3D states, is therefore E sub nx, ny, and z is equal to h bar squared pi squared over 2m times nx squared over lx squared plus ny squared over ly squared plus nz squared over lz squared. We can rewrite this in terms of h bar squared k squared over 2m, which means that we can break this up, because of the separability, into h bar squared over 2m kx squared plus ky squared plus kz squared. These discrete values of kx, ky, and kz form a lattice, which we call the reciprocal lattice, which we'll see just in a minute why that is. And we can visualize it in this way. because kx, ky, and kz are equal to some integer divided by L, and then there's a pi of course, then they represent points on an infinite lattice that is a rectangular lattice like this. So you have kx in this direction, kz in this direction, ky in this direction. And then at each lattice point where you have kx is equal to some value that depends on the integer n sub x and pi. For every point you have there, you have a point at the lattice. So for example, this might be at this point, kx is equal to, nx is equal to 2, ny is equal to 1, and nz could be equal to 1, for example. Each point on this reciprocal lattice is a discrete single particle state. Each of the single particle states can contain a spin-up electron and a spin-down electron. In order to characterize this reciprocal space a little bit better, it's useful to look at the volume of reciprocal space that is occupied by a single lattice point. And so our question is, what is the volume in reciprocal space occupied by each of these states, these individual states with nx, ny, and nz as quantum numbers? Well, we can start by drawing a rectangular box with a point at each corner. And the width of each of the directions of the box is pi over Lx, pi over Ly, and pi over Lz. That's why it's called reciprocal space, because you have inverse times the real space. Now, if you take this box, you can look at it in the following two ways. One way is to say that at each corner, you're touching one of the reciprocal lattice points. So in some sense, 1/8 of each point is inside the box. There are 8 of them. That gives you 1 point inside this box. So the box of this volume will have 1 point inside it. An easier way to look at it is to say, let's imagine we displace this box by a small amount in one direction along the ky direction. Then we displace it a small amount in the kx direction, this direction, and then we displace it a little bit in the kz direction. If you do that, only this point here will be in the box. The other points will be outside the box. That makes it really clear that this box's volume is the volume of one single point in k-space. We can write that volume as delta kx plus times delta ky times delta kz, where the delta kx, delta ky, delta kz are just these distances along the side of the box. And those are pi over Lx times pi over Ly times pi over Lz. We can rewrite that consolidating as pi cubed over Lx times Ly times Lz, but this is just the volume of the overall box that contains the electron gas. So we can write this as pi cubed over V. Now, if the solid contains n atoms, and each atom contributes a q free electrons to the electron gas, you can now start enumerating how the states in reciprocal space are populated. So, the energy depends on the distance away from the origin in k-space. So you start at the closest point and you work your way out. Electrons are fermions, so only 2 of them, spin up and spin down, can occupy each single particle state. And as we fill the states, starting with the lowest energies, the occupied states begin to fill an octant of a sphere in k-space. Right? Because nx, ny, and nz are all positive, you're only getting 1 octant of k-space. But as you move to farther and farther away from the origin, the energy will go higher and higher. So if you want to start with the lowest energies, you have to start with the states that are closest to the origin. Once you fill up with all the n times q electrons, remember there's 2 per state, and you just fill up, you reach a certain radius. We'll call that radius k sub f. And the volume of the octant can now be calculated. the volume of the octant is simply the volume of a sphere of radius k sub f, 4/3 pi kf cubed, divided by 8, because it's only one octant. Alternatively, a different way of looking at this is to say that you have n atoms times q electrons per atom, that's n times q, divided by 2, because each state can take 2 particles. And that counts the number of states which must be filled. If you now take and multiply that times the volume in reciprocal space of each state, the volume that is occupied by each state, you have the number of states times the volume per state gives you the total volume of that octant. So we now have 2 ways that we've represented the volume of the octant, and we can solve for kf cubed. If we define rho, the density of free electrons per unit volume, as the number of atoms times q divided by the total volume, then we can rewrite k sub f using this equation and this equation as 3 times rho times pi squared to the 1/3 power. We get the k cubed from here. When we bring all these terms over to the right side, we see that we have rho as nq over v, that's this term times this term, and the pi's cancel, one of the pi's cancels, the 4 cancels part of this, you get 1/2 multiplied over here, that cancels the 2, and you get 3 times rho times pi squared to the 1/3 power. Kf defines the so-called Fermi surface, and the corresponding Fermi energy, which is the energy of the outermost filled state, is just given by E sub f is equal to h bar squared over 2m times k squared. But if k squared is 3 rho pi squared times to the 1/3, then this is 3 rho pi squared to the 2/3. So this is the energy of the outermost state. It's called the Fermi energy. With these parameters and these expressions, we can now calculate the total energy of the electron gas by considering a shell of this octant with thickness dk. So I've drawn here an octant of this sphere. It has a radius k, and it has a thickness, because the shell has a thickness dk. Now, one thing to remember is the size of the box is macroscopic. So the spacing between points in k space is very small. And we're assuming that it's a nearly continuous system with very, very closely spaced states by the time we get out to a large radius k. Well, if we want to calculate how many states exist in this shell, in this octant, we can do that relatively easily by calculating the volume of the shell and then dividing that by the volume per state. And that tells us how many states. So we're going to calculate the volume of the shell first. With a radius k, the surface area of the shell is 4 pi times k squared. The thickness of a shell is dk, so if we multiply times dk, that's the thickness or the volume of a sphere of radius k. Since this is just an octant, we divide it by 8. And when we pull all this through, we get 1/2 pi times k squared dk. The number of states in the shell, then, is just this volume divided by the volume per state. Well, that's the volume. We divide it by the volume per state, which is in reciprocal space, which is pi cubed divided by v. And we get, also, we have to multiply times 2 because we have 2 particles per state. This gives us v over pi squared times k squared dk. So this is the number of states in the shell of thickness dk with radius k. If we now want to calculate the total energy in the system, we just have to integrate the energy for each shell out to the final radius, which is the Fermi radius. The energy per shell per state in the shell, since they're all at a distance k, because dk is infinitesimally small, they all have an energy h bar squared k squared over 2m. And so if this is the number of states, this is the energy per state in the shell, then the total energy in the shell is dE, which is h bar squared k to the fourth over 2m times v over pi squared dk. And now all we have to do is integrate that out to k sub f. And that's what we're going to do. We can now calculate the total energy of the gas by integrating out to the Fermi wave number. E total then is h bar squared v over 2 pi squared m integral from 0 to k sub f of k to the fourth dk. Well, that's a straightforward integral. It gives us k to the fifth over 5. So now we have 8, and when you evaluated it at 0, it gives you 0. At kf, it gives you kf to the fifth. So we have h bar squared times kf to the fifth times v over 10 pi squared m. If we now replace kf to the fifth with its actual expression, which depends on rho, which was nq over v, we get h bar squared times the quantity 3 pi squared nq to the 5/3 divided by 10 pi squared m times v to the minus 2/3. So this energy is a function of the number of atoms, the number of electrons per atom, the mass of the electron, Planck's constant, those are just constants, and then the volume to the minus 2/3 of the box in which we put the energy, the electron gas. Now, this allows us to actually do some calculations about properties of this gas. So we now have the total energy of the gas. We can calculate things that depend on the total energy of the gas, like thermodynamic quantities. Let's look, for example, at how the total energy depends on a small change in volume of the solid. So if the solid expands a little bit, what will be the total change in energy? Well, we can do that by taking the derivative. So we take dE total by dV. So if the volume expands by dV, take the derivative, we get minus 2/3 h bar squared times the quantity 3 pi squared nq to the 5/3 over 10 pi squared m times v to the minus 5/3, because we had to differentiate. V to the minus 2/3 gives us v to the minus 5/3 and the minus 2/3 in front. We note, though, if we rearrange this by taking the v to the minus 5/3 in two pieces, one is v to the minus 2/3 and then 1 over v, which is v to the minus 1, we have everything in green here is exactly the total energy, E total. And so we can replace this quantity with E total. And we get, then multiplying by dV, we get dE total is equal to minus 2/3 times the total energy of the electron gas times dV over V. But this change in energy is just the change in work, the work that's done on the gas as you change the volume. And the work that's done on the gas is just P times dV, because dV is changing, the pressure is changing as well. This is equivalent to a pressure exerted by the gas, which does work and changes the energy of the gas. So this electron gas exerts pressure on the box and can do work by expanding it. And this all comes from understanding the energy as a function of volume and all these other parameters in the electron gas. So we can get the pressure of the gas, of this free electron gas, as being minus 2/3 times the total energy divided by the volume. If we now substitute E total again with all these values up here, we get 2/3 times h bar squared times k to the f to the fifth over 10 pi squared m. If we rewrite this in terms of the density, we get that this is 3 pi squared to the 2/3 power h bar squared over 5m times the density to the 5/3 power.